So, good evening, everybody. This is Kazuya Yoshida speaking from Japan. So, tonight I will speak about the orbital manipulation things as one of the important topic of space robotics. Right. So that tonight, robotic systems for orbital manipulation. So, last week I spoke about planetary robotics, but tonight orbital robotics, and as I mentioned earlier, the two major applications of the robotics technology to the space development are divided in two application fields. One is a planetary exploration, lunar planetary exploration, and the other is robotic, mainly manipulation in an orbital environment. So my second topic is the long reach manipulator arm. So long reach manipulator arm is something like this. This is the space shuttle mounted manipulator arm for the construction of the International Space Station. And this secondary arm appears. And this is the space station mounted manipulator arm called Canadarm2 or SSRMS. So these two arms are used for the construction of the space station. And so these arms are very, very useful. And so for at the end point of the manipulator arm, that we have had a human astronaut. So that's a very interesting. So we use a human as an end effector of the such a long reach manipulator arms. So Japan also have quite similar system in a Japanese pressurized module called JEMRMS, JEMRMS. And here we have very interesting design. So the 6-joint long reach 10-meter manipulator arm, and at the end we have another 2-meter 6-joint manipulator arm for the dexterous tasks. So, but we see a very interesting problem now when we try to operate the this and the secondary arm at the end. That this manipulator arm generates the reaction back up to this base point. Then, because of that, this long reach part start vibrating. So that's a very interesting issues for the particularly in terms of the control. So this is our computer graphics simulation about the Japanese manipulator arm. And currently, yes, this arm was moving in a constant velocity, but we suddenly stopped the manipulator motion because of its inertia, and it start the such a vibration. Once we have such a vibration, it's relatively it's not that easy to dump out this vibration in a microgravity environment. So so far the astronauts operate this manipulator arm by using the joysticks. So it's a kind of the manual remote control. So the astronauts are very well trained to avoid such an excitation of the vibration. Or once the vibration occurred, they manually dump out such a vibration. But by the way, that these are the picture of the Japanese module, pressurized module, and the Japanese manipulator arm. This is already on board, and so based on the data from the operation, so we identify the flexibility of this Japanese arm. So after some motion, it shows some centimeter or 10 centimeter very low frequency vibration at the end point. So to demonstrate the situation of the very 10-meter long reach manipulator arm topped with short manipulator arm, we will see this kind of dynamics. So if we move the small manipulator arm at the end of the flexible structure, we see the vibration onto the on the flexible structure. In this case, just such a horizontal motion. But this second right-hand side example, exactly the same system, but a slightly different motion of the endpoint manipulator. In this case, the two joints are operated simultaneously, and this motion doesn't make any reaction back to the base structure. That's why no vibration was excited. So let's try something different. So for this motion, the right hand side, we have a continuous motion of the two arm synchronization. And so this synchronization cancel out the reaction. And also, we try to push the base structure, intentionally give the vibration. But we can soon dump out the base vibration. So this is something unique and special. So after the a clear understanding of the motion dynamics, we can make such an operation. And this idea must be useful to dump out the vibration of the such a space station-based long-reach manipulator arm. And this phenomenon, this physics is exactly the same as a previous example of the free-floating manipulator arm. So in a very special trajectory of this endpoint, we can generate a manipulator motion that makes a completely zero reaction back on the base. So that we can move the manipulator arm to the desired position without disturbing the base orientation. This is a very useful maneuver for the future manipulator operation. Actually, this was an example. So for both cases of the free-floating base or flexible base, flexible structure base, the equation for the manipulator part is the same. That we have again that this equation for the momentum conservation, but expand this equation for the joint angle phi dot, that we get such a formula. This happens in case we have a redundancy in the system. So the first term is called the solution for the vibration suppression control, and the second term is a component for reactionless manipulation. So by using this second term, we can generate the motion without making any disturbance back onto the base. And by using this first time, we can make a control to dump out the vibrations. So by the combination of these two terms, we can achieve such so reactionless control, reactionless motion, and also once we have a vibration, we can make a vibration damping, vibration suppression. So that's a very interesting outcomes from the momentum conservation equation. So I will not go on the details of this slide, but if you are familiar with the manipulator theory for the redundant degrees of freedom, so this is a linear algebra for square and non-square matrix. If we have the full-rank square matrix, we usually use inversion. But in case of the non-square matrix, we use pseudo-inverse and null space term. So just this fashion is the same as this equation. So pseudo-inverse part and null space component for the joint velocity. And that we get this style of equation from the momentum conservation. Then we apply this mathematics to obtain the previous result. So now I will go on my last topic. That is contact and impact dynamics. So this is again the free floating test bed in our laboratory. And so you can see heat and bouncing motion. That's a very interesting for example, high school students. So in high school, we learn about the fundamental impact theory, and by using the coefficient of restitution, and we get a very basic idea of the perfect elastic impact or perfect plastic impact or something like that. So to discuss about the impact contact dynamics in a free floating manipulation, we need to go back this fundamental physics. So the coefficient of restitution is defined for the discussion between momentum and force time product. So this is the kind of the approximation with the assumption of the contact duration. Contact time is infinitesimal. But in real situation, that we have non-negligible contact time. And in this case, that we need to evaluate the amount of contact force. So then the situation becomes relatively more difficult and complicated. So then the question is how to model the contact force. So this is a very general form. So usually we need to evaluate the depth of the penetration. Usually this is very, very small depths of the penetration at the point of contact and its time derivative. And if we put 1 and 1 here, this becomes a simple linear spring and dashpot model. So then, for example, we need to discuss for the normal direction and tangential direction. But we assume that same thing for the, in this particular case, we just assume the linear spring and dashpot type of equation. But for this tangential motion, we also assume the Coulomb friction. So then we observe the stick and slip kind of motion. But anyway, that after some discussion, we will get some good understanding of the impact, force generation, and reaction type of the phenomenon. So then looking at one practical application, this is picture for the retrieve of the Japanese transfer vehicle. This is unmanned cargo transfer vehicle, and this is the space station mounted manipulator arm, and this arm captures the this floating target. And this is very, very massive. It weighs around 10 metric tons. And if we mistake the operation, that would cause a big disaster. And so we worked together with Japanese Space Agency to modelize the capture and grasping sequence. So at this end effector part, we use a very traditional design that was originally started from the space shuttle mission. So for the end effector part, we use 3 cables. And so the grapple fixture is very simple, just the very simple pole. So then using these 3 wires, to capture the target. So this was the traditional design that has been used from the space shuttle missions and all of the space station-based missions. So we made a very fundamental study on the collision between stainless wire and the stainless the pole. So then hit and rebound type of the experiment. Then we made the relatively precise model of this specially designed for the end effector and gripper end effector and grapple fixture system that has been used for the space station related operations. So this is just a simple computer simulation for this approaching phase. This is not that interesting, but the more interesting thing is right before the grasping. So usually it has some small relative motion. And we try to keep the zero relative velocity, but maybe that this has a small drifting velocity. So then in this situation, if we try to close, capture the this end effector, so let me magnify. So in this situation, so that this fixture may hit this wire and push and back and make a rebounding motion. So we made relatively precise simulation and try a kind of the worst case scenario. So after rebounding with some with wires several times, then finally this target has an unexpected rotational velocity, then goes out from the envelope. So actually this didn't happen in the previous operation, but in the worst case, it could happen. So, so then in a worst case scenario, that this motion, relative motion of this target object was accelerated or excited, then this target get into the completely unexpected rotational motion. So this is one of the interest of the impact contact dynamics. But going back to this previous slide, previous example of the Japanese ETS-7, this was a very, very challenging operation for the manipulator endpoint control to capture a free floating target in orbital environment. And in this case, that if we miscatch the target, that this manipulator action motion may hit the target, and after that, the target can have unexpected rebounding motion and maybe start rotation. And then situation becomes very, very difficult. So I will show you a very, very simple example. So this is again our two-dimensional free-floating testbed. And here this target body is completely floating. And here we have a manipulator arm. And at the end, we have a gripper. And in this case, that gripper didn't work very well. So fails to capture the target. So please try to think what we should do to improve the situation. Maybe you think that, oh, why don't you synchronize, have a better synchronization of the gripper closeout, and we should prepare a better sensor to quickly react for the gripper. Of course, this is one of the solutions, but we have a completely different solution. So let's see the second example. So in this second example, the timing of the gripper is the same for the first case, but motion of the manipulator arm is completely different. So based on the measurement of the force, we conducted a kind of impedance control, or we could say a damping control. So the impact energy is, in this second case, completely absorbed in the manipulator motion. So if we can have this kind of the impedance control or damping control for the manipulator part, we can increase the safety of this type of the capturing maneuver. So after some discussion and investigation of the impact contact dynamics, this is just an example, but we can obtain such interesting and practical solution for safer manipulator operation for capture and retrieve of free floating target. So that is a summary of my talk tonight. And so we discussed reaction dynamics of the free floating system, and then vibration of the long reach manipulator systems. So and also we discussed about the contact dynamics, and then knowing the for the better understanding of the physics and dynamics of the system, we can derive interesting control laws for a free floating manipulator arm and also the space station based manipulator arms. So I have some reference materials. I hope you enjoy my talk tonight.